Okay, now welcome to the second class of Big Data Analytics. Last week we went through, I guess, the basic definition. Okay, we have the understanding that by big data, we're talking about data that has high volume, high velocity, and high variety. Now, the platform and the technology for handling the volume and the velocity of data is really beyond the scope of this class. It's, it's where you work for a large data architecture that has maybe like a Spark station, has a Hadoop distributed data file system and so forth. It's not something that can be replicated within the classroom. And also, chances are by the time you graduate, the technology will evolve and it will be a specialized training that you will need to attach yourself to those platforms anyway. Okay, but the V that's relevant to us is the variety. Okay, so we got that out of the way. The analytics part, okay, we talk about how essentially we're trying to make value proposition out of data asset. Okay, and the data asset, talk about how expensive data is, data privacy issue, and so forth. The reason that everybody's hungry for data is because data is an asset. The reason it's an asset is because if given enough or given the right analytics, you can turn data into insights. And insights is what gives you competitive advantage. Okay? Now we talked also briefly about, but not briefly, we talked to some length about definition of intelligence that we are in pursuit of, right? We talk about artificial intelligence in the original meaning of the word, which is something that mimics or approximates or imitates behavior of an intelligent animal, by which I mean human being. So in that case, intelligence, in particular, artificial intelligence is about trying to get an artificial system, a computer program or whatever, to mimic the behavior of or input-output response of a human being. It doesn't have to really be intelligent in the clever sense of the word. It can be something dumb. If you talk to a machine and it talks to you convincingly as if it were a human child, that's considered perfect artificial intelligence. The second meaning of intelligence is about sense of information, right? Information being that it's very sensitive. It is information that's hard to come by, information that is covert. You have to actually basically spy on that information set. So that's the meaning of military intelligence and also business intelligence. Now, with military intelligence, chances are you're talking about your enemy. Whereas with business intelligence, your counterpart would go to would have more. You have more than just your competitor. You have your clients. You have your own workforce. You have even the shareholder or the public stakeholder and so forth. Those are all your counterparts, and you're trying to get some information on their preference, how they feel about you, or how they feel about your product, and so forth. Finally, there's a computational intelligence, which is really what we are talking about. The whole premise of this class is computational intelligence, turning data into insights, into intelligent solution. Okay, solution. It's called computational intelligence because it's a form of intelligence that, even though you can understand it, and you can clearly see that human beings can be more intelligent. One guy can be more intelligent than the other. So it's very human-like, but it's not like the classical artificial intelligence where you're not just trying to imitate human beings. You're actually trying to exceed capability of human beings. Okay. Now, how do you exceed capability of human being? Not by trying necessarily to reason or logic. Progress to logical conclusion in the way that humans being don't understand, but rather in the dimensionality and degree of complexity that human cannot handle. Okay, So in this case, when I say coming up with intelligent solution, well, it's like when you were studying calculus in high school, right? You're trying to find the maximum point. And let's say maximum point corresponds to profit. If that maximization is a function over two variables, okay, you can find the best solution yourself. And that's called intelligent solution because it's a solution that maximizes profit. Problem becomes when you're trying to do this maximization over 500 variables, okay, in multi-dimensional space. Same thing with fitting data, right? You have this example in high school where you're fitting maybe a regression equation, right? Teacher would give you 20 data points, you plot it on the line, and maybe try to fit the best line, okay? The best line that fits the best account for all the variation in y versus x, that's an intelligent solution. You can easily do that if y is a function of 1x. You can also do it maybe with some kind of visualization tool, y is a function of x1 and x2. But you certainly cannot do it y as a function of 500x. Yeah. So in this sense, computational intelligence exceeds human intelligence. Okay, not because it's not because we're trying to pursue a different kind of intelligence, it's the same kind of intelligence, but not limited by human beings' capacity to operate in low dimension and small number of data sets. Okay, so that's why in this aspect, it fits very nicely with the paradigm of big data being a large amount of data. Again, even though the technical server that handles huge gigabytes of data is not something we're going to cover it here. Okay, it's more like an engineering problem. Okay. Okay, so what is the objective of this class? Remember, we talked about the objective of this class being sort of like 3-4 things. The most important thing is sort of like put you in the shoes of professional data scientists. Okay, what do we go through? What do I go through when I conduct my professional consultancy, okay, which I still do, to this day. What do I do? What's required? What's the logic? What's the thinking? Okay. Now, the second aspect is to get you into the understanding or get into a practice of coding. Now, I don't mean by coding that we're learning a programming class, right? But rather the sort of like algorithmic programming pipeline that's involved. From getting the data, finding out how incomplete or complete it is, trying to work out with some kind of visualization where the distribution is, trying to make some basic correlation view of X versus Y, see what happened, try to see if you can build machine learning algorithm that actually predicts Y better than what's been done before and so forth. Okay, so that's going to take a little bit of coding. And the project part, finally, the project part is where you're going to start to work in a maybe agile environment. Now, the agile environment is a team kind of thing. So it's going to be a team project. Having said that, we'll see. You might learn a lot more if you actually do individual projects. So we'll play by ear. We have to have. There aren't that many of you, so we can play before. We can think of course. Let's see how that goes. Right. So let's go to the coding part. Now, the coding part, every one of you is entitled to a semester of mathematical license. It's very expensive to license. So, but because you're part of the class, then you can register and so forth. It's there. Mathematica is not a free program. It's a closed environment. It's a bit like iOS. So that in particular, it's not an open kind of free for everyone. It's not like Python. So analogy would be Python would be similar to Android. Okay, you have a bigger community, which is the good side. The thing about Mathematica is two things. Purely as a programming environment, it's a lot more consistent in the sense that it's designed it's monolithic. You have a company that designs software. You don't have like a community of contributors. Okay, so that's good and bad. Okay, it's good because it's consistent. It has manuals and reference, easily accessible and explained to you. But the downside is, of course, if the functionality isn't there, you haven't got it, right? Whereas with Python, if the functionality isn't there, maybe you go to community that build some library and add to it. Now, there are some people who add to library in Mathematica, but really it's nowhere near as robust as the Python community. The other thing, which may not be relevant to you at this time, is that Mathematica is more powerful in terms of the analytical computation, because what it does, it treats object inside the program as a computable object. Now, this doesn't mean anything to you, but in programming, you have to have some kind of data structure, right? Data structure, like this data structure is a number, and what can you do with it? You can multiply it and so forth. Well, Mathematica is an abstract analytical engine, so it can treat the object as a mathematical entity, and it can check whether or not you can do certain operations and so forth. The good example I can tell you is that you can literally give a mathematical equation and ask it to do derivative, analytical derivative, differentiation, integration in calculus. That's something that's not doable in Python. You can do it numerically. Okay, you can always do anything numerically. You cannot do it symbolically. Okay, so, and the third thing that's good about Mathematica is that because it really is, it was designed for very difficult problems in physics. So for simple problems like fitting, statistical regression, it's kind of routine almost. So what the program does is, because some of these things are so, kind of no-brainer. So they make it a high level. So you can just say generically, I want to do a regression, and it would just do the automatic steps for you, because regression is no rocket science. So a lot of this is automated. Okay, whereas with Python or a pure programming language, everything is on the same plane. So it doesn't matter if you're doing something really complicated or something really simple. If somebody has made a library, it's there. If somebody hasn't made a library, it isn't there. And there's no high level approach. Whereas with Mathematica, certain thing like, well, let's fit data points and see if they can cluster together. This is something that's so routine, they just make it a high level description of it. So you can literally say, take this data, build a neural network. That's it. That sort of thing. And this is good for a lot of bite-sized students who are not going to be professional programmers. So if they go into like sustainability track, they go into healthcare, health science, they go into smart cities and so forth. This is something that, they don't want to get to the nitty-gritty programming. They can do a high-level test of concept. So it becomes something very good in terms of proof of concept, test of concept, and prototyping tools. Okay. Now, today it's very simple. Class is very simple. I'm going to, I actually have, my plan here is to actually write interactive textbook in analytics and machine learning. Okay, so it's going to be like a textbook, but in digital form, you can actually go into the individual equation and press enter and do some calculation and plot and change and all that. So that's my long-term plan. One of the chapters from there is to actually give the basic Mathematica operations necessary for a lot of machine learning tasks. Okay, so I have that. However, for this class, I thought what I might do is to go even one step below that. Just give you the bare bone minimum. In other words, let's think of today as walking in, you know nothing about Mathematica. In fact, you don't have to know anything about programming, absolutely zero about programming. And in 2 or 3 hours' time, you walk out with the bare necessity to start to communicate with the computer what you want it to do. Okay? Again, we have an unequal asymmetric relationship, as it were. You and computer, you're not friends, right? You don't care about the computer's well-being. You only want to communicate to the computer in terms of the instruction. You want the computer to do something for you, right? So it's that kind of instruction. So it's like teaching you the language you need to talk to your tools. Okay, it's not a language that you need to talk to your mom, your dad, to say how grateful you are. No, it's a language to teach you to speak to your tool and say, please do this for me, please do that for me. I need something done. Okay, and that's the language we're talking about today. Okay. So first, okay. Now this is the I will give you this kind of mind map at the end of the class, I think, but it's better for you to actually try to key in what I show on the screen. Okay, so you guys have the program starts, except maybe one of you, two of you, if you might have to share the computer. Okay, right. First, let me go to this thing called environment. Okay, environment. Oops. A kind of yeah, this thing is always blocking my path. Okay, right. Okay, I just want to say that there are three things I want to talk about. The environment is about, if you're going to work with Mathematica, what is your what are the screens you need to open up on your desktop? Let's put it that way. Okay, if you work with Python, not only do you work with your own program develop, sort of like a IDE, interactive development environment where you put the code, you also have like a website like GitHub that people share codes. You have, help, you have a library and open up. So this is sort of like, what have you got to work as an environment? So first thing I want to mention is that in terms of paradigm, okay? Now, the first thing that you have to think is the paradigm is how you talk to your computer, okay? And there are a few programming paradigms in life. My PhD was based on object-oriented paradigm, okay? It's not just the code that I use, it's actually how I model my problem. So it's usually you have a problem, you turn it into computer code, and then you use computer paradigm to guide your programming. But my PhD, my own PhD, is actually goes the other way around. The computational paradigm ends up informing how I model my solution. Okay, so my paradigm is object-oriented. It's not here. It's not here. It's not a straightforward. It's not easy to do in Mathematica. In fact, nobody does it. Okay, so first thing you have to understand is computer programming language are separated into families. Okay, some families follow one paradigm. Some families follow a few paradigms. Some, Mathematica follows essentially two paradigms, roughly speaking. Python is also a little bit like this. Now, you can do object-oriented programming in Python, okay? And professionals do that to organize their code, okay? But for your point of view, there's only two paradigms. Paradigm meaning, how do you talk to your tools? How do you talk to your tools? Okay. Functional programming is the main paradigm that you're going to use in Python and Mathematica. So in fact, if you're not a computer scientist, you only need to know functional programming, and that will probably serve you the rest of your professional lives. That would be my guess. Okay. What functional programming is, again, thinking of the word programming as dialogue you have with the computer with the view to ask the computer to do things for you. Do this, do that for me. Okay? So when you program a computer, you're asking the computer to do certain things according to certain instruction set. But how do you frame your instruction? Well, functional programming means you think in terms of mathematical function. Y is equal to f of x. Okay? Now, let me say that again. Think of a function. What's a function? Function is a transformation of input x into output y. Okay? Mathematically, you learn that, right? Maybe y is equal to x squared or something, okay? Y is equal to sine of x. Well, think of that. Except instead of just sine and exponential and logarithm, everything you do is a function. So let me give you an analogy. An automobile manufacturer is a function that turns metal, comma, rubber, comma, aluminum, okay, that's your x's, into y is a car. Okay, see that, right? And you can say, well, you got that car from the showroom and you don't like it, you want to modify it. You take that car, the factory built car, as X. You go to a tuner body shop, okay, put in a turbocharger, I don't know, tune the engine to make it faster, lower the suspension, okay. That's also a function. The input is a factory standard model, output is a race rally car. Okay, so from that example, what do you know about function? You know that function can be anything. You know that for each function, it has a set of input it expects, right? If I give metal and rubber and aluminum to a car manufacturer, it knows what to do with it, right? But if I give the car factory, an auto factory, a jug of milk, it wouldn't know what to do with it. It's not the input it expects or it can use. It's useless, okay? So there's an input definition, there's a definition of the transformation that happens inside the factory, and there's an output. And the output itself is no special. There's no such thing as ultimate output. Everything is also an input. Okay, so think of that, right? Think of that. So that's functional programming. The way you talk to your computer is to say, I give you an X. Please use that F of yours to give me a Y. That's number one. Okay? Now pay attention. It's very important. That's one level of communication. What's a deeper level of communication? Anybody? Well, let's say you have a maid. Okay? You and older ladies, you don't get around, so maybe your son or your daughter has you a maid. You want an omelet. Okay? Your maid is your computer. Take an egg, make me an omelet. All right? The maid has a built-in function called making an omelet. Okay? That is functional programming. However, the maid is so flexible. Not only can she make omelet, she can make a whole bunch of other things she hasn't made before. But you have to give it two instructions. One instruction is the recipe. This is how you make souffle. Remember that. Then the next day you can ask for souffle. So that becomes added on to a capability set of your maid. Same thing with functional programming. There are built-in functions we'll go through today. Okay, and so what is functional programming? Okay, I'm not going, I'm just going to describe, you can take your note. Number one, use it as a calculator. Okay, use it as a calculator. That's it. The maid knows how to make an omelet. Please make an omelet. She comes prepared. You don't have to show her anything to say, please make an omelet. That's using a built-in function. Number two, you can put built-in function together, right? So, for example, I think in Chinese, you have this dish where you fry an omelet and then you put in the soup. Well, let's say the maid knows how to make soup and it knows how to make an omelet. Then you can teach this maid. The only thing you need to do is to say, make an omelet, stick that omelet into your soup. Those two things are well-defined steps. Well-defined step. Making an omelet is a well-defined step. Making a soup is a well-defined step. All you do is just pipe them together. So that's second level of functional programming. And first level programming is like a computer, and like a calculator. Do this. It already knows how to do. But it doesn't know how to, it knows how to make an omelet. You knows how to make an omelet, how to make a soup. But this is the first time somebody's asked her to make an omelet, then throw it into the soup. This combination is new. So even though the basic component is built in, the combination, the pipeline is not. Okay, so that's a second level of functional programming. A third level of functional programming is what I told you earlier, where you actually came across a recipe for making a souffle. Your maid doesn't know how to make a souffle. You actually teach her first how to make a souffle. Okay. And once your maid knows how to make a souffle, next day you can ask your maid to make a souffle, or maybe throw a souffle in the soup. I don't know. Okay. So that's what's called functional programming. The second, I'm just writing because it can be done as well, but it's clumsy. It's not a natural way of speaking to Mathematica. That's called procedural programming. Procedural programming is when you actually tell the steps, and this is where if you take like basic, in the old days, they used to teach this language called basic in grade school. You see a lot of this. It's, the for loop, the do while, if, then, that sort of thing. So it's kind of giving the nitty gritty, right? If the egg is raw, throw in the frying pan. If it starts to smell burn, then you take it out, that sort of thing. So it's giving the procedure. Okay. Now, you can say the procedural programming is underlying everything, because at the end of the day, computer has to do something by procedure, right? The point is that with Mathematica, it's a higher level language. So a lot of procedure are embedded inside the function. So instead of having all this for loop, while loop, if, then, and that, really big detail kind of thing, a lot of it is just wrapped inside. Okay. For example, I'll give you an example right now that you are going to see. When I was maybe your age, if I want to select a best model, the best model for regression, I have to, for all the class of model, try to fit and then select the best, right? So that kind of procedural for all the model class, try all of them, check which one, and blah, blah, blah. But if you think about it, you can wrap the whole thing into a function. That function called find the best one, right? And that becomes a function. So you can think of functional programming in this sense as a higher level. And that's where we are. Okay, so I only write down that, procedural programming is part of Mathematica construct, but chances are, if you are using a lot of if, then, for, while, and, you may be not programming it the neatest way. Okay, the neatest way. Same with Python. Now, these two things apply with Python. Okay, the only addition I would give is that, again, to handle code complexity, there's also an object-oriented way of speaking to a Python. I'm not going to cover object-oriented in this class, but it's a beautiful paradigm. Fine. So that's the first thing I want to get across. Second is in terms of the platform itself. There are actually, this one here is what we're going to learn. Yeah. Oh, sorry. มีพี่พูดมาตลอด Gotcha. Oh, where are we? Where's the Zoom command? Where did it go? Zoom commandอยู่ไหน More, share. Oh, share screen. Okay. Is this the screen's been showing all this time? Okay. Right. So this here is Mathematica. It's computational kernel notebook. It's a notebook, basically. That's what you open up. By the way, well, not a friend of mine, but my senior, when I was at Imperial, was really big into Python. But Python, when I was your age, didn't look like Python you look like today. It was sort of like, it had very poor user interface. And then some Python programmers saw Mathematica's kernel, and based on that design, make a Python kernel style notebook. And that's what chances are, if you learn Python from my side, we'll use that to teach you. And that's called Jupyter Notebook. Jupyter Notebook is modeled after Mathematica Notebook. Yeah, so it looks exactly the same thing. It has a little bracket on the right-hand side. You can round bracket together and so forth. So it's modeled, it came from this. So that's the main thing we're going to use. Now, the reason I put two more things in the platform is there's this thing called Wolfram Alpha. Okay, this is something that can, I'm going to demonstrate how to use it well. Wolfram Alpha, you can think of it as a search engine, except instead of searching like Google, where you search over the web, it searches over the database of information of all the quantitative information. So, for example, if I Google Thailand, okay, it would just go find the pages that say something about Thailand. Whereas in Wolfram Alpha, if I Google Thailand, you're going to see that in the database of country information, what have you got? Like the population, the COVID rate, the area, geographic, the history database, all kinds of stuff. These are all sort of like digitized, mostly quantitative data set. Okay, weather and all kinds of stuff. And this will come up. And once it comes up, again, it's not a static like a Google page. When a Google page, you search something, it's a page, right? Here becomes a pieces of information. So if you search Thailand, comes up with a population, you can double click it and say, okay, let's make a historical plot of population of Thailand, whatever. Okay, so it becomes a computational object. Okay, but this is something that's built on Mathematica. You see that. And finally, these are peripheral tools that helps, like demonstration tools that help archive other people's work, tools that helps me do scientific publication, tools that help me create tutorial and so forth. So today we'll just focus on that. And finally, there's this thing called repository. Now there are three large repository that's built around Mathematica, just like GitHub is a public repository. Well, in Mathematica, again, it's not, it's a closed system. So it has three repositories. One is a function, mathematical function. It's called a function repository. One is data. So this would be equivalent to something like Kaggle, except it's curated. So you know exactly the format, you know exactly the coverage. We'll go over that. And by the way, these are all the websites to link to that. And finally, there's a repository on neural net. Now, a neural net just covers all the machine learning, mostly neural network-based model that's has been invented up to date. Okay, now I'll tell you later, but a neural network is like, it's like a model that has to be tuned to a data to be useful. So in neural network repository, you find two kinds of neural network. You find this, the framework of the neural network. It's like a model that hasn't been tuned to any data set. Then you also find a trained neural network, meaning the model is already tuned to a certain data set. But what's good about it is that even though it's tuned to a data set, you can tune it some more with your data set. And that's what's going to be the future way of working. When I was your age, training a neural network means giving a neural network function. And starting a set of function with some parameter and then set the data to it. Nowadays, and in your lifetime, that's hardly ever going to be how you work anymore. You are going to get a neural network that has already been trained with some data, but not exactly relevant to your situation, and you train some more. A good example would be something like a model that has learned to predict tuberculosis from the scan of lungs of 2,000 patients in America. Okay, well, Americans are human, so are Thai, but we don't have exactly the same physiology. Okay, and nationally we have different smoking rates, so the data set is not exactly the same. So if I want a model that predicts tuberculosis in Thai population from looking at the scan of the lung, okay, I would not start from scratch. I would also not use the model that is tuned to American lung pictures. I would take that as my starting point, right? And then I'll do a little bit of manipulation and then add the Thai lung to it. Okay, this is how we work. Okay? So it's very important that, so you think of this thing as function as a pure math, right? This is sort of like function, this is a data, and you can think of neural network as a repository of function that has already seen data. Think of it that way. Okay, right. So that's the environment. Okay, again, just develop over time. Now, again, you walk in here, even though you have, and I like to do this as well, even though you have a lot of, some of you may have programming background, you've done things a lot of coding, you may not have taken the time to actually stop and say, what exactly is the program doing? Or what am I doing to the program? In other words, you're not kind of like thinking of how you program because you've done a lot of programming. You know how to do it really well. Okay. So this is going to be something that's going to benefit complete novice, somebody who hasn't done any programming whatsoever, as well people who are fairly proficient in programming, but never stop back there. Okay, this is the kind of programming I'm going to do. They're actually different paradigm or different way of organizing your programming thoughts. Okay. Yeah. So let's start with what exactly, okay, is the element. Well, like I said, I'm going to be talking about the functional programming paradigm. And that's the main syntax. That's the main language, phraseology, how you phrase your thing. So you don't say, computer, please do this to me, or do this for me. You don't say that. You say, computer, I want Y. And to get the Y, here's an X, and use that F. Right? So that's how I speak to my tools. So basically, there are three things that you need to know at the very basic. What do I mean by variables? And then, what do I mean by function? And like I said before, right? There are built-in functions that came with the software. It's like an addition. And except they have, instead of Mathematica coming with add, subtract, multiply, and divide, it comes up with 5,000 additional mathematical functions, maybe 10,000 by now. Okay. And then you have what's called user-defined function. Okay. And no surprise, your user-defined function is going to be built from built-in function. So learn the built-in function first, and then put them together, right? So think of that the Chinese omelet soup thing, right? The built-in function is making omelet. Another built-in function is making soup. You want to make an omelet soup, so you call these two functions in sequence. Now, if you happen to like this a lot, and you're going to use this all the time, are you going to say to your maid, make an omelet, put it in a soup? Or are you actually going to say, make an omelet soup? Right? That's exactly what a user-defined function is. Right? Once you put making an omelet plus put it in a soup, you're going to use it so much, you might as well wrap it and call it make me omelet soup. And that becomes save function. And that's how complexity builds. Okay? The reason functional programming is so ubiquitous right now, okay, it's no accident. Okay? You didn't have computer scientists sit around debating in a room. I like object-oriented programming. I like functional programming. I like this. I like that. And who's the best? and the best one wins and everybody uses that. No. It turns out that functional programming is very adaptable to the way the modern AI-driven computational intelligence, artificial neural network world works, because you can keep piling on complexity in a very natural way. You can also pile on complexity with object-oriented, but after a point, it becomes very clumsy. Okay, it's like object-oriented is elegant, but it has too much overhead. It's like if every time you want to do additional, if a company wants to build a new division, it actually have to create a new company as a subsidiary and create its own corporate enterprise. It's a lot of overhead in object-oriented. Okay, now that's the reason why functional programming kills it everywhere today. There's a reason why. There's a reason why. It's not just it's a popularity contest, but there's a good reason why functional programming beats object-oriented programming today. Okay, now I can say that because I myself love object-oriented programming, but the world evolves. Okay, so let's go to variable. Yeah, there's a lot of preamble today. Okay, what do you need to know about variable? Well, a variable is the in and the out, right? It's what you give the computer as input. It's also what you get out of the computer as output. So it is the object that you're handling, and not object-oriented, but it's the thing, the very essence of what you want done. Okay. So first thing I have to cover is, well, you can't, I can say do something to this, and I can point to it. Well, I can't point to it in a computer. I have to name it. So the most fundamental concept is assignment. Okay, you have to assign a name, basically. Okay, so this, type in this. Okay, you can, again, you can copy me, or I'm just gonna, I did this to save time, so I put this in a sort of like a slide. So think of this as a slide. So right, so this is what you should write. X is equal to 1. Okay, so again, if I wrote this. Okay, I wrote this. Now what you do is you shift enter. So type in X equal to 1. Say X equal to 1. Okay, just like that. Right. X is equal to 1. Shift enter. Okay, what happened now? What happened? It's very important. First of all, you notice that this is an in and out, and there's a number 1, 2, 1, 1. So this is the first input. This is the first output. This is the first. I started this program. I haven't done anything. This is the first action I did. So this is a counter. This, by the way, is the kernel. This is where the Jupyter notebook copies. So you can see that if you double click this input, you hide the output. If you double click here, you show the output. You double click the output, you show the input. Now this becomes handy because once you get to the provision programming, you may build an app, right, to show you the client, and then you just want to show the app, so you just hide the input. So this thing is one set of things. Okay, so I shift enter. Nothing else has been done, even though I wrote it, just a text. This here is the output of this operation. What is another output of that operation? What's the result? Well, I don't know if you noticed, but before I did this, X was in blue. Okay, in fact, if I do Y equal to 1, notice Y is blue, equal is black, 1 is 1. This is, well, this is by convention. Okay, it's to guide your eye to say, what does the computer know? Computer knows 1. Computers know equality, In this sense, it's an assignment. Computer doesn't know why. Okay, it doesn't know why, so it's blue. Anything that you haven't defined to the computer doesn't know. Anything the computer doesn't know is blue. But once I enter it, okay, so I haven't done this. I put in Y. Y is blue, right? Shift enter. Y. That's it. I give it Y, give me back Y, because it doesn't know what it is. It's sort of like what? Okay, but instead of saying what, it just said, oh, you give me Y, I give you Y, because I don't know anything else better. But what happened to X? If I put in X now, I get a 1. Because now I define X as 1. Okay. This is something called definition. The thing you need to know about Mathematica is that by default, same as Python, it is global. In other words, if I actually start a new program, new notebook, okay, new notebook, and I put in S, I get a 1 here. Okay, it's everywhere across this instance. The only time this would forget is I close the program. Okay, now there's a way of getting rid of this. So this is called assignment, and this is called recall. Okay, now, yep. How do you use the scope? It's called module again. So by default, it's global, and it is permanent. It's permanent until you turn off the program. Now, this is different. I put X is equal to 1, 2, 3. So assignment is not undoable. It's not permanent in the sense that you can override it. So I make another one. Except, look, there's no output. The reason there's no output is because I put this semicolon to kind of like silence. So it sort of like turns the page, as it were. So that's all you need to remember. And this is useful because otherwise, if I have a lot of this, you know, Y is equal to 4, 5, 6. And if I didn't do this, input, output, see, input 6, because actually it's input 6, but actually 2 output. So output 6, output 7. Yeah, and this is X, this is Y. So this is, if you have a lot of this, it's very noisy. So I'm just gonna shut up. Okay, fine. Okay, it's very easy. Now, what's this? X is equal to X minus 3. This works from right to left. In other words, X is assigned to X as it was. So what was X before? 1, 2, 3. So X minus 3 is 120. So you assign to that, right? Now this is a shorthand. Instead of X is equal to X plus 5, you say X plus equal to 5. So you can do that. What's the value of X now? What do you think? Well, it's 120 before, right? And you plus equal to 5, so it's 125. This is what happened. Notice this is equality twice. So 1 equality is an assignment. 2 equality is the question. Is it equal? Okay, so it gives it true. If I say something like this, false. Okay, right. So that's very easy. Multiplication, 2 times X. All you have to do, you don't have to put multiplication, just put a space, 2X. Okay, so that's as easy as it gets. Again, this is going to be, depends on how you view this the value of this exercise. For those of you who've done a lot of programming, this is extremely painful because it's so slow, right? Yeah, but again, everybody's on the same page. You understand that a single keystroke has a multiplicity of actions. Okay? And this is by design. Okay? Somewhere else, it may not be the same. Okay? So, yep. Louder bit, go ahead. Yeah. The reason it's global across is because each computation is consideration. So you can actually start a new kernel and do something else, and you have parallel machine and all that. So it can get a little bit tricky, right? Now, this is the most basic thing, is a variable that is a number, right? A variable is a number. So, but I can do something else as well. So let's go back to here. Instead of x is a number, I say x is equal to the color blue. Okay. Now, again, notice the reason x is black is because it knows the value already. So I'm going to be reassigning it. The reason this one is black is because it's a defined name. It comes with the program. So it knows what the blue is. Now, it's a capital letter. So if I write in small letter, it doesn't know. Okay. So all the built-in function and names start with a capital letter. Okay. You need to know this. Okay. And you can't have you can't have empty space. You also can't have minus sign in hyphen. In Python you can, by the way, but in Mathematica you're not allowed. Okay? And you must start with numerical number. You must start with the name. The variable must start with alphabet. You can't start with number like this. Okay. Okay. So x1 is x is equal to blue. What happened? Enter. Blues. Okay, so this is the output. Oops, right? Can you see? Yeah, the output is the blue. Okay, it's a blue. X is a blue, right? So it doesn't have to be the number in that sense. So right away, this is the B in variety of the data, big data, right? It's a very tiny, silly little thing. But now look at what happened when I double click on this little blue sign. See that? It says that this is actually a function called RGB function. Let me double click it. So it becomes a, sorry, where'd I go? Where'd I go? Where did my blue go? Oh, my blue. Okay, I'm just calling blue. Okay. In this case, I'm not assigning, so I double click it, right? So what's blue is RGB, right? So now, if I want it a little bit more purple, I can just slide it over and maybe something like this. And okay. Oops. So now it becomes something else. It's not so blue, right? Can get some advanced opacity. So this is what I mean by computational object, right? It's not a number, it's an object. That object can be as complicated as you wish. So this is what I mean by, like in Python, as with every language programming, you treat an object as a data structure. This here, it recognizes the object. This is actually object-oriented kind of way of thinking. This thing has certain attributes to it. This thing has certain property, certain thing you can do to it. What can I do to this? I can change its ratio. I cannot do anything else. I cannot make it bigger. I cannot make it smaller because it's not an object called circle. If I have something called circle, I can make it bigger, make it small. This is a color. I can't make color bigger. I can make it more green, less green. Okay. So that's one thing. Okay. If it's one number, what do you call it in mathematics? Scalar, right? One number is a scalar. Okay. In this case, it's one thing. It could be a number, it could be a color. Now, the second is called list. List is where you deal with more than one thing at once. Now, it has two meanings here, so pay close attention. Notice I type in here list, open bracket, 12, blue, and both. Type in exactly like I do. Okay, and shift enter. Okay. Notice the object I have will be curly bracket. 12 is a 12. Nothing fancy there. Blue is this thing. again, and both, because I put in double quote, it gives you a string. So a list is a way of putting one thing after the other. That's it. Now, a lot of time, you don't have to do this. If I want to make a list, again, I can just use square bracket. Sorry, curly bracket. Right? Now, let's say my x, I'm going to redo my x a lot. Okay, then x is equal to this. Again, gives an output, right? If I don't want the output, I put in semicolon like before, so shut up. Okay, and I call x. This is recall. I get this, right? Now, what is important about a list is that it's an ordered sequence. Because it's an ordered sequence, I can specify particular element. So I want just the word boat. I do this. X, okay, key in like I do, open bracket, square bracket, okay, do it twice, and put in, well, the position you want. You want the first one, you want the second one, or you want the third one? Let's say I want the third one. Get both. Okay, so this is how you access element of a list. Yeah. Sorry? Oh, yeah. Mathematics starts with 1. Python starts with 0. That's the difference. Okay. And so you can access this element, the third element, or if you have a long list, you want the last one, you just go -1. Right? So this is going from the back. What's -3? What do you think that is? That gives you 12, right? Because it goes back -1, -2, -3. So if you put minus, it goes on the back. Right? Sometimes it's more useful because big database, I want you to look at it. So that's that. That's simple. Nothing complicated. Now, let's make life more complicated. Instead of having one bracket of items, I have one bracket inside brackets. So it's nested. So in this case, okay, let me just do this. I define this thing called x is equal to a bracket of bracket. It's a list of lists. Okay. Now, the first list has how many elements? 2 elements. This is the first element. It's also a list. The second element is also a list. So guess what happened when I define this and I call 2 and 1? Anybody? Just common sense. Yeah, 2 and 1 would go the first element, the second element. That's number 2. And you 1. Okay, that's it. You're right. Oops. Great. Okay, that's great. Okay. So that's how you create a list. That's how you create a list. Now, sometimes you don't want to create a list manually. They are built-in functions. Okay, and this is similar to what's called list comprehension in Python, except it's much easier to write. I use this thing. By the way, I already started using built-in functions, as you noticed, right? So table of I, now read this. Just type in exactly like I am typing right now. Table, open bracket of I, comma, and then this. What this tells you, what this function does is say, create me a table or a list of I going from 1 to 3. Okay, I going from 1 to 3. Now, the reason this is so useful. Okay, again, I'm teaching you the basic, but it's one of those things where nowadays, I've been doing so many data science projects professionally. I still use this thing. So that's why I know from life it's useful. Okay. So that's it. Table of I going from 1 to 3. Simple as that. Now, this is common sense, right? If I put in I and 3, that means I want I from 1 to 3. What if I don't want I from 1 to 3? I want I from 2 to 5. Then I put in another one. So this is another style you might want to get used to. Sometimes you can put just the bare minimum. But if you want, and Mathematica is going to give you a common sense. Common sense. What's the most usual thing you can do? If you give me 3 numbers, well, it's going to be 1, 2, 3, right? So it doesn't have to write 1 here. I don't have to say 1, 2, 3. I can omit it. And it will interpret it as 1, 2, 3. Now, if I want to be more specific, I can say 2 to 5. Now, so 2 to 5. Now, what if I don't want consecutive? I want to go 2 to 5, but instead of 2, I can do that. And this is what this is. Going from 1, and you can start even non-integer. From 1 to 2, 1.2 to 34.5 instead of 6.7. 1.2, you add 6.7, you get this number. You add this number. Now, it doesn't get to 34.5. Why? Because you cannot add 6.7 integer times to get that number. So it stops at 28. Because if you add this 6.7 to 28, you get something bigger. So this is how you create. Okay. Now, what if I don't want to iterate 1, 2, 3, 4, 5? I want just a collection. I do this. I going from A to B to C. Now, I have this for you to refer back to because it's going to be very easy once you use this to handle the data. Okay. Now, last week I mentioned to you, right, that we're going to be working with maybe picture data, voice data, and so forth. But 80–90% of your application is going to be tabular data, meaning tables number. Okay, that's why things like tables is going to be so ubiquitous. Okay, because this is how you keep a bunch of data. So you can have 500 rows of 3,000 columns, whatever. Okay. Now this here is a table of tables. So what do you think is going to happen? By the way, Mathematica doesn't care if you put enter. And I do this just to make it look nice. So key that in, table, open bracket. Now notice I put this A here in front of IJ. What do you think is going to happen? I've never said before what A is. Right? I've never said before what A is. I'm just going to be a table. Okay. The outer loop is 1 to 2. The inner loop is 1 to 3. What's going to happen? Well, A is blue. What? Yeah. By the way, if you pay good attention, this kind of indexing is color teal. It helps when you write a big program to notice that this is something you refer to. This is what you get, right? Notice the outer loop is 2. So there are 2 things. 1 thing, 2 things. So you can call it like. I may not use this very much. Okay. Right. And the inner loop is 3 things. So 1, 2, 3. Right. Again, it doesn't know what A is, so it just repeats. A11, A12, A13. Okay. Because, again, table is a built-in function. So you can imagine that when Mathematica came out, there's this function called table, right? And I like to create this table of tables so much. I'm going to create a function called array as a table of tables. Well, sometimes user-defined function, becomes so ubiquitous that in the next iteration, Mathematica will just make it a built-in function. Okay? Well, chances are array is already in Mathematica 1.0, but this is what happened at sequential version. So Mathematica 13.0 has 10,000 functions, whereas Mathematica 5.0 would have maybe 500 functions, or whatever. I don't know. Okay, so this is one of those things where I want to do this. I just make an array of this 2, 3. Oops, sorry. Yeah, array. This is array of 3 things. This is array from 2 to 3. This is array of 2 things by 3 things. So I spend a lot of time trying to come up with the smallest number of examples that would demonstrate the variation in the program. So, this is not by random. I put in a lot of thought. I spend a lot of time selecting particular choice of value. So this here, it's not this. This is array of A going from 2 to 3. So that's 2 and 3. Oh, sorry, from 2. Array from 2 to 3. What did I have A before? For some reason on the spot, I kind of got lost there. But the point is, if I put the bracket around it, it's actually not giving the count, it's giving the dimension of the object. So it's 2 by 3, 2 things by 3 things. Now, this thing doesn't look nice. Doesn't look nice. Yeah, doesn't look nice. So there's a function called format. So this thing is where, if you know linear algebra, you see this a lot. So the same array, if I put matrix form around it, yeah, I think this is what I wanted to do, was here. There, that's what I wanted to. Okay, it's actually 2 by 3 matrix. Yeah. So this is how you would write it in a mathematical textbook, but in a computational word, this is this. So a matrix is an array, rectangular array of m row, n column. In the computer speak, it is a list of m objects. Each object is a list of n numbers. That's it. So now you've got 2 things. Now you've got 2 things. Yeah, you've got assignment of basic single thing, and you have list of things. The list of things is used 2 occasions. 1, generically, it's just a list of things. So I can say table, comma, chair, comma, bar. And that list, open bracket, 3 will give you bar. Okay, it's just a list. But mathematically, if the list is a list of same thing, and that same thing happens to be number, what have you got? A vector. Okay, so a vector, remember the vector gives you dimension. Let's say 3-dimensional vector, it gives you coordinate, right? 3, 4, 5 is to go to x direction 3 units, y direction 4 units, and go up 5 units. So 3, 4, 5 is a vector, right? You can represent that using a list. In fact, because Mathematica most of the time is used for mathematical operation, when you see a list in Mathematica, chances are it represents a vector. And it can do things that vectors usually does. For example, it can do dot product. So if I did this, and you know about dot product, right? Yeah. So if I did this, A 1, 2, 1, 3, 5. Okay, watch this. Dot X, Y, Z. What do you think is going to happen? Yeah, you see this little dots here? Again, a list is just a list, but most of the time you can actually use it as a vector. So in this case, you can think of vector as doing dot product. So it's going to be 1 times x plus 3 times y plus 5 times z. Oops. Oh yeah, I forgot. Let's make it a. Let's make it x1, x2, x3. Okay. Now you ask me how to get rid of this. Let's do this. Clear. I need to clear x. What else I do? I need to clear y, I think. Okay. So now x and y becomes blue again. And this gets clear across the board. So notice that this is kind of, you have to think of the way the language design is designed for mathematicians and physicists who want to not type in a lot. So the common sense say, if I have a list of things that of the same dimension, well, I can do dot product, right? Then it's okay, it's allowable. Now, certainly something is not doable like this. This is going to give you error. Because why? The dimensions do not match. Right? So the way Mathematica does is that give me anything, if it makes sense, I'll do it for you. Okay? And I will assume the most common sense way. So that's why open bracket I, comma 3 means I going from 1 to 3. Because common sense say, well, let's start at 3. I start at 1 and go to 3. So that's why this, it seems like, well, sometimes you put in a lot of omission. It's because you can think of professional mathematicians and physicists who don't want to type in a lot of things. So now, the other thing you need to know is what's called association. In Python, this is called dictionary. When I say it's a list, right? How do I refer by, how do I refer to each element of the list? I refer by position, right? What if I want to refer to list by name? Okay. In that case, I have this thing called association. Now look, this association, I just happen to do this. This is my association. Association, the letter R point to red, the letter G point to green, and the letter blue point to blue. This is my association. And it gets you this funny thing. So I can actually do this as well. This is just as I had a curly bracket. The other bracket you need to know is this funny bracket. Left less than equal to vertical partition, and then vertical partition. So this is kind of a funny bracket. That's it. No more funnies. This is all you need to know. Okay. So the curly bracket is a list, but this is an association. When you have this, let's say I call it X. Okay. I like to keep using X. So X is equal to this. Now, instead of going by position, what if I want this number? This thing, how do I say it? I call it by name. So I go X, open bracket, the name is green. Dictionary, yeah, in Python it's a dict. Okay. So this dictionary is very useful, and if I want to, there's a special function. Sometimes I create a list and I want to know what are the names and what are the values. So these are the keys and the values. Key is the name, basically, right? So key is R, G, and B. The values are the colors. So, okay. Now, in Python, you almost cannot do anything in Python unless you load this data frame object called pandas. Okay, for those of you who have not taken Python today, it basically pandas is Python trying to swallow Excel. Okay, think of Excel, right? You know Excel is a spreadsheet, right? Well, Python is created as a generic language. So everybody try to use it, but a lot of people who try to use it have to work with people who are used to working with Excel, right? In Excel, you can do row, you can do column, and you can do pivot and some basic operation and so forth. People are used to doing that. So what Python does is create this thing called pandas, okay? Which is kind of like Excel inside Python. That's what it is, okay? Well, an Excel inside Mathematica is called dataset. Well, dataset mathematically is nothing more than a set of lists, right? So it's a table just like before. So I can do this as well. If X is this data set, sorry, X is an association. The data set is a little bit like that, except it looks more like Excel, right? You see how it looks like table? It's tabular kind of friendly thing. And this is something that I sent you a paper that my son did last week, right? On COVID data. That one takes the data from our World in Data live feed from that, or the latest feed of that day, put it in a data frame. Okay? If you were to do this in Python, it would be in pandas. Okay, so you can do group by and all kind of stuff. So that's why it looks like this, but it's the same thing. Y and X is the same thing. X is an association, Y is a data set. So data set is a more Excel friendly way of doing things. Okay. So you can do the same thing. So X and Y is exactly the same thing. And that's why if I did this, I actually get through, even though they're actually different objects. Yeah, this is just that. But depends on how you think. My way of thinking data set is not always the most elegant way of handling data. Having said that, it is a very common way. Just like when you program in Python, it's very common that at the beginning of the file, you see import pandas as PD, imports numpy as NP. Okay, it's sort of like a standard way of handling tablet data. Yeah, of course. Yeah, I've got well, yeah, let's take a five minute break.